So, how to obtain your perfectly function back again? We need something called pulse functions. So, we're going to draw another graph with our obtained values we have stored in our discrete function. And we are drawing our values like this once again. And then we have a value over here, another one here, etc., something like that. Now, we want to obtain our original function again. What we're going to do is use pulse functions, because pulse functions can reconstruct our function, well, almost perfectly if we choose the correct pulse function. And it's important, something about pulse functions, they have some cases, but a pulse function in itself, if we integrate over its surface, it should be perfectly equal to our sampling period. If that is not the case, then we run into big problems, because then our whole pulse function does not modulate our function back again. So what is a pulse function? A pulse function we can actually define as the following. It is 1 if our t is bigger than minus half of the sampling period, or if it is lower or equal to half of the sampling period, and 0 otherwise. Well, if you want to do that for our function, so let's do this in another color, then what it actually looks like is like this. It's just a square, where this has a length of our sampling period. And we're going to apply this to every data point that we see. So if we do that for our function up here, we get the following boxes that just connect our dots like this. So this actually just models our function. Well, not very good, actually pretty bad, but it actually does kind of a nice job. But of course, we can do way better than this. Introducing another pulse function, which we will call the triangle pulse function, which is defined as 1 minus the absolute value of our t divided by our sampling period if t is in between the positive and negative sampling period and 0 otherwise. How this pulse function looks like is just a triangle like this, where this length is 2 times the sampling period, but the surface of this triangle is once again just the sampling period, and that's important. And if we apply that to our data points over here, not like that, excuse me, like this they will. Because they reach all the way to the next stem. And what this actually does is, if we add up all these values of the yellow lines, we would actually get something that looks like this. It is just linear interpolation. We just connect every dot to the other one, which is kind of better. It doesn't go in steps anymore. It is a better approximation of our function. we could have some other pulse functions. There's also the sawtooth function. But the best function that remodels our function perfectly is the sinc function. So if our pulse function is equal to the sinc function. And sinc function is defined as the sine of t divided by, sorry, not t, actually, if you want to normalize version, which is used a lot, it is pi over the sampling period times t divided by pi over the sampling period times t, which looks a little bit like an octopus. And at 0, it is not defined. Wait, it's going bad. This. At 0, it is not defined, so define at t is 0 to be 1, or just the value in front. It is a times this. If you actually take the limit of it, it will actually code to that value, but we're not going to talk about that right now. And if we multiply this with every stem that we have in our data point, or every data point that we have, we actually obtain our original function back. It goes like this. Ooh. Damn it. It was something like this. Oh, the green one should be a little bit shorter, but whatever. So this is the best pulse function that you can get. It is the ideal one because we get our original function back. In the syllabus there in chapter 13, I think, it is proven why it is the best one. But however, for now, this is just explaining what pulse functions are, and if you need to use them, that you know how to use them.